The research aims to develop a speaker-independent speech inversion system that estimates velar and glottal activity for nasality prediction. It utilizes Nasalance as the ground truth, derived from oral and nasal acoustic signals. The system is trained on a dataset including high-speed nasopharyngoscopy (HSN) data for direct measures of velar opening and electroglottography (EG) for source features. The study demonstrates a significant correlation between Nasalance and HSN signals, and the system can accurately estimate velar and glottal activity for improved nasality prediction. The study analyzed speech material from 8 subjects, focusing on the Nasalance parameter as a measure of velum port closure during speech production. This parameter was computed using root mean square signals from oral and nasal microphones in a nasometer setup, normalized to a range of 1, 1. To validate the Nasalance parameter, high-speed nasopharyngoscopy (HSN) was synchronously collected from 2 subjects, providing a direct measure of VP port dynamics. The HSN data, with a sampling rate of 1 kHz, was compared to the Nasalance parameter, sampled at 100 Hz, by linearly interpolating the latter to match the HSN intensity trace. Pearson correlation coefficients were computed, showing strong negative correlations between the 2 measures, indicating that as the VP port opens, the Nasalance parameter increases, supporting the use of the Nasalance parameter as a proxy for VP closure. This study examines the timing patterns of nasality and voicing parameters in speech, focusing on the relationship between nasalance and velum lip coordination during syllable initial and syllable final nasal consonants. By analyzing the words homie and home-e, the authors observed differences in velum movement and lip velum coordination. The results, as shown in Figure 3, demonstrate that the Nasalance parameter replicates the timing patterns described in previous studies, with respect to the lip aperture tract variable, LaTV. The study also extracts the voicing parameter from the electroglottography (EG) signal, using the envelope of the EG signal to capture voicing activity. The speech inversion system used to analyze the audio signals takes the combined audio signal from oral and nasal mic signals, downsamples it to 16 kHz, and segments it into 2-second-long segments. The input audio representation is then converted into auditory spectrograms (AudSpec), to provide a unified multi-resolution representation of the spectral and temporal features of the audio signal. The model architecture of the speech inversion system is based on a temporal convolution network (TCN), optimized using the mean squared error (MSE) loss. The model consists of 1D convolutional layers, dilated CNN layers, and upsampling and average pooling operations to match the time dimension of the input spectrograms to the target time dimension of the TVs. The hyperparameters and corresponding values used to fine-tune the model are listed in Table 3. Overall, this study aims to provide a comprehensive understanding of the relationships between nasality, voicing, and articulatory speech parameters, and to develop a robust speech inversion system that can accurately analyze and represent speech signals. This research paper introduces a novel dataset aimed at estimating velar and glottal activity in speech, with a specific focus on the estimation of a validated Nasalance parameter as a proxy to velar TV using a speaker-independent speech inversion (SI) system. The authors employed temporal convolutional network (TCN) modeled to estimate the Nasalance parameter from auditory spectrograms. They trained 2 SI systems, one with additional source features as targets, SISF, and another with only the Nasalance parameter as the target, SINOSF. The results indicate that the SISF model outperforms the SINOSF model in terms of Pearson product moment correlation (PPMC) scores for correlations between the estimated and ground truth Nasalance parameters. The paper also delves into the hyperparameter tuning process for the TCN model, which involved a grid search to find the best parameters based on validation loss. The chosen parameters include a learning rate of 1E3, batch size of 64, atom optimizer, and exponential LR rate scheduler. The model has around 1 million trainable parameters, takes approximately 8 minutes to converge, and can be accessed through a GitHub repository. The authors plan to enhance the performance and generalizability of the current SI system by training on data from a larger group of subjects in future work. They also intend to validate and fine-tune the nasalance parameter as a proxy to the velar TV, and conduct further experiments to understand what the DNN models are picking as source-filter interactions that are ultimately helping the overall SI task. The study concludes that having a SI system to estimate parameters directly related to the velar and glottal constrictions can be highly beneficial, as it gives an almost complete articulatory level representation of speech, which can be useful in diverse speech applications, such as articulatory speech synthesis. An accurate, validated speech inversion system would also be a significant breakthrough for researchers with little or no ability to collect articulatory data directly, enabling hypothesis formation and testing that will motivate more targeted studies. I'm sorry, but I do not have the capability to perform this task for you. I am happy to help you with any other queries you may have.